Okay, welcome to the final session of Thursday. Leading us off is Peter Behroozi, going to tell us about multi-phase enrichment of the universe.
Right. Is this on? It's on now. Can people hear me? Am I amplified? Okay, good. Great. So thanks to the organizers for allowing me to present today, and also for allowing me to show up for only one day of the conference. I'm very sorry about that. I want to talk a little bit about metallicity evolution in galaxies. But before I do that, I think it's helpful to talk about the ecosystem of empirical models, and there are a lot related to the work that I do. So I just want to give you an overview of what all is going on in empirical model land. And empirical models go by a couple of different names. Models, machine learning, or my preferred framing is combining observations to figure out what it is that galaxies are actually doing. And so we have models for what are supermassive black holes actually doing, led by Ho and John. We'll talk about that tomorrow. We're having models in preparation for what galaxy dust and color is doing, and we'll talk a little bit about that tomorrow. I'm going to talk about this one, the metallicity evolution of galaxies, in an empirical model today. That's work done by a student at NAOJ in Shigaki. And Han Guo has already done an empirical model for H1 and H2, so neutral gas around galaxies as a function of halo mass and other properties. And of course, this is all building on work that I've done and others have added to with the university. So let me today talk a little bit about gas around galaxies. We all have the same qualitative picture, which many people have talked about before. Gas comes in from large scales, reaches the existing galaxy, gets blown out by feedback. Some of that recycles, some of that goes out to larger scales. And that's sort of the picture that we've all come to see and love. Except when we look at simulations, there's less to be said. So this is, of course, from the Agora project. If you look at many different simulations, you see different distributions of metals around galaxies. And sort of the understanding of why this diversity occurs is very simple. A lot of simulators have all tried to match to galaxy stellar mass functions or the same stellar to halo mass relation. And for a given amount of gas, you can form the same amount of stars in a couple of different ways. So you can either have sort of small bursts of energy that send out gas before it can form a lot of stars, and that gas recycles quickly and deposits most of the metals in the state. Or you can drive huge outflows that never come back. So that driving a huge outflow requires more energy, and so you spend a lot more energy that way, but then the gas takes a really long time to come back, and so you end up still forming the same amount of stars in the galaxy, then the metals go to very different places. Basically, there are many different ways of getting the same stellar to halo mass ratio and just moving the gas around to different places and moving the metals around to different places. So actually understanding what real galaxies are doing is helpful to constrain models of galaxy formation, especially hypersymmetry. Okay. So I want to talk about how we do this empirically to figure out what real galaxies are doing. And for that, it's helpful to look at equations. I usually don't show equations, but today it's hard to avoid talking about equations. So I want to focus on the total amount of metals in the ISM, interstellar medium. And so let's talk about that. So the total amount of metals is going to be the mass of the ISM times its metallicity. If I ask how does that evolve over time, it's the time derivative, then there's sources in space. So there's a source of gas coming in to ISM, which will bring some metallicity from CGM or from the high EM. And then we have another source, which is stars forming inside the galaxy. So some of those will explode and deposit metals inside the ISM. Some of those will explode and deposit metals to larger distances. So I'm going to subdivide metals produced by the stars into two categories. One category is outflows, which don't come back to the ISM. And another category is sort of gas that gets recycled back into the ISM. How many metals are produced by the stars? It's a yield factor, little y times approximation rate. And I'm going to say some fraction FISM of that comes back. into the ISM, and some fraction 1 minus FISM gets ejected out of the CGM. And then the last term, this missing space here in equation, is gases or metals that are locked up and belong to the star. So some fraction of the metals are locked up and belong to the stars, and that sort of completes the metal puzzle. There are a lot of terms here. I don't like a lot of terms. I always like simplifying equations. And so if I ask what are the most important terms in this equation, it's this one right here. So the inflow coming from the CGM or from the IGM is going to be much lower metallicity on average than in the ISM. And similarly, the fraction of stars to the total amount of gas is going to be small. So the amount of gas or metals locked up in the stars is also going to be small. So if I make the approximation that both of those are about 0, then what I get is EDT of metal mass is just effective yield times star formation rate. You can integrate that and get this equation down here. So the total amount of metals in the ISM is just average return fraction times the total metals produced by the star. So here I mean the total stellar mass produced as opposed to. And we can solve this for what fraction of metals on average get retained by the galaxy. And this is something that you can then go out and measure for individual galaxies if you wanted to. So why, of course, you have to assume or calculate in some way that you can measure a stellar mass of a galaxy, you can measure gas mass, especially for those galaxies, and you can measure a metallicity of that gas. Okay? Right? So everything of this right-hand side is observable and constrainable. And so with some approximation, we could get this fraction of individual galaxies if we wanted. There's no sort of magic about empirical models. It's making it possible. It's just that this is all coming from. So let's talk about how we actually modeled the full thing, because in practice we want to be careful and we do want to account for metals getting locked up in stars and so on. So our approach, a more detailed approach, is we start with the dark matter simulation that gives us halo merger and growth series. We add in galaxy masses from the universe machine, and so very, very briefly, the universe machine constrains the stellar to halo mass ratio along with other things like redshift, using many different observations of the mass function correlation function and so on. Philosophy about it, I'm happy to. There's stories about how that works. The next piece is masses of ISM components. That's H1 with a factor for helium, and then also H2 masses, and that's coming from the neutral universe machine model. And I just want to briefly talk about that because I haven't introduced that before at this conference. The basic idea is that you can measure, in many cases, all different properties related to H1 or H2, and try to combine them together to get a model that fits everything simultaneously. Where is the information about the relationship between H1 or H2 mass and halo mass coming from? Well, in many cases, you can measure as a function of galaxy mass what the H1 or the H2 mass is doing. Again, that's directly from observation. And then the stellar to halo mass ratio from the universe machine is telling you how does that H1 or H2 mass then relate back to halo mass. And so this particular empirical model combined a number of different observations. For example, 21 centimeter observations of H1 at low redshift, times of CLA observations at higher redshift. Also, all kinds of different measurements of H2, including phase, alpha scale based. So there are a lot of different observations that went into this redshift. The basic idea is if you can measure as a function of stellar mass what the gas mass is, then you can use the universe machine to convert that into gas mass as a function of halo mass and redshift. So I've talked so far about stellar masses. This is ISM masses for H1 and H2. And of course, we also need to have metallicities. So we measure metallicities in several different ways. For ISM metallicities, specifically H2 metallicities, we assume that's other H2, so the ionized inside the galaxies. And so that's mostly measurements from emission lines calibrated using the beam method for galaxies that have that available. And James Webb has made that available for now every galaxy from which that's before. For the H1, we use GLA metallicity. And that also is the amount of H1 gas that is sort of self-consistent. So if you notice at the top here, our conclusions are only sensitive to the product of GISM and MISM. The total amount of metals probed by GLAs is the only thing that we care about. If you think we're getting sort of excess gas in GLAs inside, that's fine as long as the total amount of metals are I'm happy to talk about that later in questions. Questions about GLAs versus metals in the atomic. Okay, and then last we have some CDM metallicity measurements using historical lines. Cool. So we have measurements of sort of all these different pieces out to redshifts of about 5-ish. Sometimes a little bit lower, for CDM much lower. So we can try to combine all of these to get a picture of what fraction of metals are retained in the ISM. The first thing that we assumed was that the metallicity of the H1, of the atomic gas, was the same as the metallicity of the molecular gas. And that failed miserably. So we didn't initially try to fit the metallicity of GLAs. We just tried to fit the metallicity of H2 regions as well as CDM. And what we found was that the average metallicity of the H1 regions as probed by GLAs was much, much lower than predicted by sort of a well-mixed model where the H1 and H2 metallicity. Then we allowed the metal return fraction to be different for the H2 and H1 regions. And that gave us not only much better, but much more sensible fit. I don't know if you noticed in the left-hand top panel that there were some sort of weird things going on in resolution. But of course, also this model is very, very strongly preferred in comparison with the H1 metallicities. And still sort of reasonable in comparison to the CDM metallicities. There's a little bit of the modeling at the highest end. We're not sort of counting metals just as satellites. So the most massive galaxies is contributing to sort of other places. So the conclusion is, what do we find that matters for galaxy formation? We actually get a very simple picture, which is that the total amount of metals returned at average to ISM is independent of redshift and just depends on the potential L depth. So I've shown here on this axis the circular velocity, maximum circular velocity of the halo, which is a redshift independent probe of the potential L depth. And you can see here that despite the uncertainties given by observational uncertainties, basically, you get roughly the same return fraction of metals into the ISM at potential L depth, and as you expect, as you go to higher and higher potential L depth, you have a higher fraction of the metals produced by the central galaxy remaining in that galaxy. And the other thing that we can get is basically an understanding about the split between H1 and H2. We're still sort of thinking about why this is occurring. There are, of course, uncertainties in all the components and sort of alpha CO, as well as what does it mean to CSA versus ISM and so on. And some of that could be playing into this. But at first order, we found that a decreasing fraction of the metals are deposited in H2, whereas an increasing fraction summary here. Metals produced by galaxies seem not to be well mixed, at least between GLA probe H1 and H2. And then other key point is the fraction of metals returning to galaxies, ISMs, just depends on potential depth.
Plenty of time for questions. Mark in the back.
Right. So I'm wondering how to physically interpret the finding that the H1 and H2 are different, because, I mean, we know when we study the formation of molecular clouds that, you know, there's very rapid cycling back and forth between the atomic and molecular phases. And so should I interpret this as basically a proxy for galactocentric radius, that the H1 is, you know, the H1 is basically outer galaxy where there aren't many molecules, and the H2 is inner galaxy, and that's really what's going on, or do you have some other interpretation you can give to that? Because in general, right, I mean, stuff that is in a molecular cloud now will almost certainly be H1 30 megayears later, and vice versa.
Yeah, that's a good question. So the first order, yes, galactocentric radius matters, but if you look at pictures of local galaxies, where's the H1 and where's the H2, you see that spatially they're in very different locations. And it's not just galactocentric radius, but sort of where you are in the spiral arm versus collisions and sort of all kinds of structure there.
Right.
Yeah. Yes. 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 Sure. Yeah, so what I say is they have to be different metallicies, especially at redshift 0, where we know we're actually measuring ISM as opposed to a higher redshift. And I think it is just galactocentric radius, but if you go to larger distances, then you have lower metallicies at that time. Yes.
Okay, other questions? Say your name if you would.
I'm Omri from the Hebrew University. I just want to comment on the only equation you've shown and neglected the inflow term. Now, there was a recent paper by one of the postdocs in our group that found that in massive galaxies at high redshifts, you can have substantial mixing of hot CGM gas and brought in by the streams, and the flux can increase by a factor of 3. And that can be also metal rich. And I don't know, compared to the other terms, maybe Neil will know better if it's negligible or not, but the inflows can be metal rich because of this thing.
The reason I say that is that we tried 4 different models where the inflow came from the IGM with basically 0 metallicity or slurs, or it just came purely from the CGM, where the CGM metallicity was, or we allowed mergers to bring in gas into the ISM, so 3 metal-enriched satellites merged, we like dumped them into the ISM, or said no mergers ever go into the ISM. And they all gave almost exactly the same. And the reason for that was that the CGM metallicity ended up being much lower than the ISM. And so most of the metals in the ISM came from stars as opposed to coming in. So yes, in detail, you found slight shifts. The overall picture of, for example, constant return fraction with redshift 3.
Okay, chair's privilege. I'd like to ask a question. What about the assumption that the DLAs are necessarily the best tracer of ISM-H1? There have been many cases of people discovering DLAs, going back to look for the actual galaxy, and not finding it or finding it quite, far away.
Yeah, so the answer is yes, you are correct. So if you look, for example, at simulation, so here's an example from TNG 100. If you look especially at massive systems, you can find cases where the DLA level column density is associated with some inflowing as opposed to there being any sort of associated galaxy. Counter to that is that it actually doesn't matter for us at all. So what matters is basically what matters is this product of DISM with MISM. And so if our masses are wrong, because we're getting some sort of DLAs associated with inflow, that's okay because our total metal budget is basically unchanged by counting that. So we're measuring the ISM metallicity in the same gas that we're counting for the total ISM mass, then this product, which is equal to the total amount of metals So our conclusions about FISM then alter.
One more question? Okay, let's thank Peter again.